Okay, so today we will be looking at AC steady state analysis. What does AC steady state analysis mean here? It's an alternating current signal. Yes, yes, there will be an office hour tomorrow, same time at 12. So our signal is an AC signal. Uh, we will be looking at single frequency signals, sinusoidal signals for simplicity. Because sinusoidal signals are way easier to deal with when it comes to derivative or integration. The integration of the sinusoid and the derivative of a sinusoid are known already. So this is going to be from chapter 9 and chapter 10. So at the beginning, we will refresh your memories about terminologies used in AC signals. Here we have a time domain AC signal. It's a cosine signal. We will be using the cosine as our reference when it comes to the sinusoidal signals. So in this signal, we have the amplitude Vm is the 12 volt here. That's the voltage. We have the phase phi as 10 degrees, which is the angle right. So if I am to write this VT, so it's going to be Vm cosine. This 50 is the radial frequency, omega, which is radians per second, 50, which is here, omega t plus phi. So this is the phase shift. This is in degrees. This is the, for simplicity, we use unit of degrees here. Omega is the angular frequency, which is radians per second. So you have to be careful that you have here, this is degrees, right? And this is radians per second. When you multiply it by the time, seconds, this is going to be a rate total. The unit for both of them would be radians. So you have to be careful if you, for any reason, would like to add them. You have to use the same unit. But this is how the angular frequency is given as radians per second. Now the period t here from, so if this is, let's say, if this is a cosine, so if this is a cosine, the period here is from the beginning to the end, right? So this is t, which is also the inverse of the frequency. So t is 1 over f, where f is the frequency in hertz, number of cycles in second. Or in time, you can say the period here, t equals to 2 pi over omega. That's going to give you the second. The time from the beginning to, for one full cycle, the time it takes for one full cycle. Okay, so this is, we said this is the amplitude here, volts. And the whole thing is volts. Okay, so we've seen this before. You have seen this before. One cycle of oscillation. Yeah. So we call it a steady state because it does repeat itself. It is a periodic signal that repeats itself. So this periodic signal is gonna will be giving you the same response. So that's why we call it a steady state. Now let's look at this example here. We need to find VT and IT in the circuit. Now, before we go there, we need to understand the phasor representation. So when we say this signal has a sinusoidal signal, and as I said before, that this sinusoidal signal is a periodic signal that it repeats itself. So for me, what is important to know are two things of this of this time domain signal. It's important to me to know the amplitude of the signal, and of course to agree upon one reference type of sinusoid. And we said that we will be using the cosine as our reference, the positive cosine as our reference sinusoidal signal. Which means if we have two sources that one of them is cosine and the other one is a sine, we have to convert the sine first into cosine and then go into the phasor. And we'll show you what does the phasor mean here. Those signals, if you remember, if I am to represent this signal on here on a polar in a polar representation, this signal can be the, and of course based on the cosine here, I have a phase of 0, right? So right here, I have this 10. This is 10 and phase of 0. However, this is going into an angular frequency of omega. So this is rotating. This is as a periodic signal, sinusoidal signal represented as the follows. As follows, the amplitude here, the angular frequency, which is 4 here, radians per second, right? And the phase was 0. The starting phase was 0. So now in phasor representation, what I'm going to do, I'm going to freeze the time at t equals 0, for example. Which means that for me, the whole circuit will have the time frozen, and then what are important to me is the amplitude and the phase. So for me, this signal now, if I go to the frequency domain and represent it in phasor representation, for me it is it is only enough to take the amplitude. So I will say Vs now in phasor, it will be capital, only the amplitude 10 and the phase, this represents the angle, right? So the phase here is 0 degrees. So this is for me important to represent this voltage source. So I will be representing this voltage source by this phasor representation, which is basically only the amplitude and the phase. The frequency, the angular frequency is going to be the same. We're only dealing with circuits that all the sources have the same frequency. So the frequency, the angular frequency for all the sources that will be used, and our circuits in AC steady state will have the same angular frequency. So omega is going to be the same. Yes, go ahead.
When you say phase, you mean the offset from zero, the angle offset from zero, I assume, right?
Just a second. I can't hear your voice. Maybe. Uh,
Right. So when you say phase, you really mean the angle shift along the time domain. Like if you start at zero, your phase is zero. But if you move the function like 90 degrees to the right, the phase is 90 degrees.
Can you guys hear his voice? I cannot hear his voice. Okay, so let's see what's going on here.
Hello? Is that better?
Just a second. I'm trying to. Okay, this is hold on. Hold on a second. Okay, try now. Can you repeat your?
So when you say the phase, you mean the angular offset. You mean
That's correct. That's correct. Which is basically, in this case, if I am to compare this with my general form representation of a time domain signal, which is here 10 cosine 4t plus 0 degrees. So this is my phase. So the offset here, if you want to call it, is the offset in phase would be 0 degrees. So that's why what is important to me when I do the analysis on circuits that have AC signals, of course, as I said, with the same frequency for all the sources. What's important to me in calculating or analyzing the circuits is the amplitude of that source and the phase of the signal, which is the phase offset here being 0 degrees. So this is going to make my life easier when it comes to dealing with the AC signals, as we will see later on. So this is how we're going to do it.
you're
So
saying there is no frequency modulation. We always assume constant frequency.
yeah, absolutely, because this the whole purpose is to understand how do those elements which are, let's say, we'll see later on, capacitors and inductor, which are a frequency dependent components, act in circuits. So the whole purpose of this AC steady state is to look at unmodulated single frequency sources or signals in circuits. Okay, so we have agreed upon using phasor representations when it comes to sources, going from time domain into the frequency domain. And not just that, we also need to, know that those components that I'm calling capacitors and inductors, they are frequency dependent components. So let me start first with the capacitor. So that's the capacitor that we have seen earlier, and we know in this capacitor that in time domain the current is C dV t over dt. So if I assume that the voltage is of a sinusoidal signal, uh, let's say V is A cosine omega t, right? Then the phasor representation to this would be V capital. In phasor, we always use the capital A 0, right? This is the phasor representation to this signal. Now, if I calculate the current, which is ICT here, being the derivative of this sinusoidal signal, so I have here A d over dt for cosine omega t, then I c would be here. Before I do this, let me first calculate the derivative and show you what do we mean by using the reference, because here once we do the derivative we're not going to get a cosine, so this is going to be a omega minus sine omega t, right? So here the signal would be minus a omega sine omega t. Now for me, in order to go from sine to a cosine, it's very important to use this simple way of converting sine to cosine. So let me call this one sine theta, and this one is cosine theta. And the direction here for going in theta, this is the positive direction for theta. So for me to go from sine into a cosine, so sine theta, if I want to go to a cosine, this is going to be going counterclockwise. So this is going to be cosine, whatever angle I have, minus 90 degrees, right? This is for sine. But what we have here is a minus sign, right? I have a minus sign. So if I want to go minus sign, so this is going to be the minus sign. If I want to go from minus sign into a cosine, in this case, I have minus sine theta. It's going to give me cosine theta plus 90 degrees, right? Here is minus sine. If I am to go from minus sine into a positive cosine, then I have to add 90 degrees to my angle. So here, this is the direction of the positive. So let's say this is for going from cosine to sine. I'll be adding 90 degrees because all of them are 90 degrees, right? All of them are 90 degrees. So it depends on the direction of motion. You'll be either adding or subtracting. So going from minus sine theta into cosine, basically you have to add 90 degrees to the phase in order to get a positive cosine. So in this case, IC t becomes a omega. Now this minus sine, whatever angle, would be replaced by a cosine, whatever angle, plus 90 degrees. So this is the current derived from this relationship that we have seen earlier in time domain. Now, if I am to write phasor representation for this current, then IC becomes a omega C. Of course, we drop the C here. So here we drop the C, CA, CA, A omega C 90 degrees. So this is the current and phasor representation, right? Now, yes, go ahead.
So is that omega times C or omega of C?
Omega times C. A omega C. So this is the amplitude now for the current. This is the new amplitude for the current after taking the derivative of the voltage signal, right? So now we need to define what's called the impedance of this capacitor, which is basically the voltage divided by the current. Remember, in DC circuits, we use the resistance to define the relationship between the voltage and the current. At that time in DC, capacitors was an open circuit, inductors was a short circuit, right? In DC. Now in AC, they do have what we call an impedance. Their impedance now, they do have a definite impedance that we need to find, which is basically the relationship between the voltage and the current in than higher than frequency of zero. So after we found the current in phasor and we have the voltage in phasor, now we can calculate the impedance for the capacitor. So in this case, we have ZC equals to A0 divided by A omega C 90 degrees. So A is going to cancel. You're going to end up with ZC for the capacitor as 1 over. I will rearrange and call this one J omega C. Can somebody tell me where did this J came from? Where did it come from? What is J here? J is the imaginary number. But how did, yes, that's correct. So the 190 degrees is indeed the J. How? If you recall, in complex plane, if I am to represent a rectangular complex number, let's say this is an impedance of 0 plus J, which means this is J1, right? If I am to convert this complex number from rectangular representation into a polar representation, then I would be finding the magnitude, which is 0 squared plus 1 squared, right? And the angle would be tan inverse of 1 divided by 0. So in phasor representation, this impedance would be 190 degrees. So this J is the complex number in rectangular format. This is what we call rectangular format, which is basically the real plus J plus the imaginary. This is the rectangular format, and this is the polar format, which is basically the magnitude and the phase. Yes, go ahead.
You said impedance capacitance is 1 over j omega c. Is this related to capacitive reactance by chance?
Yes, this is the what we call the reactance. That's correct. Any impedance, any impedance is made of a real and imaginary. In general, impedance is made from a real and imaginary, right? So let's say x plus j y. This is the what we're seeing here is the rectangular representation of a complex number. If I am to convert this into a polar representation, I would be getting the magnitude and the phase shift, if you want to call it, or the phase offset from the zero uh, from the uh, horizontal axis. So here, if I am to convert this one into the polar, what I'm going to get is the following: x squared plus y squared. This is going from rectangular into polar, and then tan inverse y over x. Now this y is called the reactance, and this x is the real, right? So since we have introduced the capacitor, and we know the resistor, so I will talk about the resistor and the capacitor. Once we're done with the inductor, we will add the inductor as well. So the impedance is the general representation for for the definition of the resistance the current is seeing when traveling through this device. So in general, this impedance is made of a real part and an imaginary part. For resistor, for example, I only have the X. Resistor does not have uh, an imaginary number. It's all real. Now, if I am to write the impedance for the capacitor, an ideal capacitor, again, it's an ideal capacitor, does not have a real number. It does have only omega c. Sorry, 1 over j omega c. If I am to take the j up, then this is going to be 0 minus j over omega c, right? If I am to keep the positive here, then I can say j times 1 minus 1 over omega c. So this is the reactance part of the capacitor. Now, once we do the inductor, you will see that the reactance part of the inductor is positive. And that's why when you have a capacitor and inductor that are in series, they tend to, to cancel the reactance of the inductor and the reactance of the capacitance. They tend to cancel from each other. The greater in magnitude is the dominant. We were going to come to this, but let me first, before we go there, let me continue the inductor. Now, for the inductor, if you recall, the relationship was VLT equals to L di t over dt. Now, if we take the current now as ILT to be A cosine omega t, then the phasor representation to this would be IL equals to A 0, right? We've agreed upon that any signal in AC steady state, it is important to be represented by the amplitude and the phase offset, or the phase shift, or phase offset, or phase, we call it phase. Now, if I want to calculate the VLT, then it will be L A d over dt for cosine omega t, and this would be VLT again minus L A cosine omega t omega sine omega t, right? So this is the signal after taking the derivative of the cosine omega t. And as you can see here, I have this negative sign that I can get rid of when I convert my sine signal into the cosine, which is the reference that we talked about. So let's put this again here. So we have here sine theta, we have cosine theta, and we had positive going this way. So this is my minus sine theta, and if you recall, we said that if I am to go from minus sine into a cosine, I would be adding. So I have minus sine theta. This equals to cosine theta. Theta is whatever angle was in already at the at the beginning, plus 90 degrees. So here, this VLT becomes L A omega cosine omega t plus 90 degrees. Now, if I want to go phasor here, then this VL capital, always remember that you make it capital in phasor and you remove the t. You are not in time domain anymore, so you remove the t. One of the common mistakes that I have seen during all those years, that some of the students will still keep the t. So it is VL equals, this is going to be L A omega, and the phase offset here would be 90 degrees. Now again, if I am to introduce the impedance for the inductor, which is VL divided by IL, then the impedance for the inductor would be L A omega 90 degrees divided by A 0 degrees. Then A cancel with A, and then I can say that ZL is J omega L, the famous impedance representation. Or you can say that here it's a pure reactance, only imaginary, omega L, only omega L. Now, if I am now to, just for, for illustration purpose, want to put everything together and show you what is going to happen. If I have this circuit that is made of a resistance and an inductor and a capacitor, that all of them are connected in series, right? So this is R, This is L, this is C. So if I am to find the total impedance for that circuit, what do I have? I have Z total equals to ZR plus ZL plus ZC, right? So let's put all those together. What is ZR? We said that ZR is a pure uh, resistive. So ZR here is R. What about ZL? We said ZL is pure reactive. So here it is J omega L. And the unit is impedance for all of them. What about ZC? ZC is 1 over J omega C. Now, if I want to move the J to up, then this J becomes J, and of course it becomes minus. But if I want to give the minus to what is inside, right? Why did I do this? I'll show you why. Because when I put them all together, it will be clearer to you what happened here. So this is going to be R plus J omega L plus J minus 1 over omega C. This is indeed the same as minus J, right? Minus J. But I did this just to show you that if I take the J now outside, the reactance of the inductor and of the capacitor will can from the opposite sign, so they tend to cancel each other. So I have here omega L minus 1 over omega C. So this whole part is the reactance, and this is the real part of this impedance. So as long as omega L in magnitude is a greater than, so if F omega L is a greater than 1 over omega C, the equivalent circuit is going to be inductive. It will act as a resistance with an inductor connected to it in series. So this is the reactive would be positive, it would be inductive, right? The reactive part, the reactance would be positive. Now, if is less, the reactive part would be capacitive. So here, this is going to be positive. The reactive part here is going to be negative. Why? Because as you can see, they're from opposite signs. So whichever is greater in magnitude will dominate. If omega L is a greater in magnitude at that frequency, remember this is a frequency dependent. So this is how does this change in practical way? In some devices, it does not change. That's why you have your limiting factor is the frequency to some component, and that's why in circuits design we tend to go toward smaller, more uh, in dimensions. We shrink the dimensions in order to get rid of those parasitics, because sometimes you can have a capacitor, right? A capacitor that its limiting factor is limited by by the frequency. So you cannot change, you cannot do anything about it. Your limiting parameter here is the frequency. It has a self resonance. You cannot use it as a capacitor beyond this frequency, for example, because it will be changing from capacitor into inductor.
Sure.
Yes, go ahead.
So again, does this relate to the tank circuit? Because when you have the capacitor inductor in parallel, this is what you need to create alternating current. And when the two reactances equal each other, that's the resonant frequency.
Well, that's the thing. It depends. If they're in parallel, they're gonna create an infinite impedance, right? For that frequency, they're gonna block this frequency from entering. When they are in series, they're going to create a zero reactance part at that frequency. So series series resonator is different than parallel resonator. Both have they have different applications, right? Okay. So let's move on now and uh, talk about that example that we have started with. We need to find VT and IT for that example. Okay, find IT and VT. As I said, in this simple circuit, the first thing we need to do before doing anything is going into the phasor representation. So this is Vs again, time domain is 10 cosine 4t. So 4 is my angular frequency. And the phasor representation here would be capital Vs equals to 10, 0 degrees. What else I need to convert? I need to convert this capacitance from zero point 0.1 farad into an impedance. This is the capacitance in farad. Remember, we don't use capacitance in the circuit. We use the impedance of the capacitor. So this is one of the common mistakes that I have seen. Be careful. Do not do this mistake. You're going to lose a lot of points in that uh, in that question if you have it. So ZC is 1 over J omega C. So the impedance ZC is 1 over J 4 times zero point 0.1. So ZC is minus J 1 divided by zero point 0.4, 2.5 ohm. Keep in mind, capacitors always will have a negative impedance. Why? Because the imaginary number is in the denominator, right? Once you move it up, it becomes minus J. So this is the impedance for the capacitor. The impedance for the resistor is 5. So here I have ZI R is 5 ohm. And I need now to find the voltage and the current. So how do I find the voltage and the current? Can somebody tell me? So let me redraw the circuit and show it to you in Phasor. So I have here 5 ohm. Capacitor is minus J, 2.5 ohms. Get used to circuits with the impedances, and this one is 10 0 degrees. So can somebody tell me? Remember now, this V here is capital, and this I here is also capital because they're all now in phasors. We need to calculate them in phasor. So can somebody tell me? Okay, so you need to find the Z net and then divided by, okay. So this is one of the, he said, I equals to Vs divided by Z, Z net. And then he wants to find the Z net, which is 5 minus J 2.5. Now keep in mind that impedances are treated exactly like resistors when it comes to series and parallel. So if you have two impedances in series, regardless of what's inside this impedance, then Z net is Z1 plus Z2. If you have
Alright.
two impedances that are in parallel, Z1 and Z2, and you need to find the Z net, then the Z net would be, or I can say the 1 over Z net equals to 1 over Z1 plus 1 over Z2. Yes, go ahead. Yes, no questions? Okay. So this is the Z net, 5 minus J 2.5. I just added them because they were in series, right? They were in series. So if I want to calculate the I here, then I have my voltage and phasor representation, polar format, and I have my Z net and rectangular format. So what I should be doing is convert the Z net into the same format. So I have here Vs as 10 0 degrees divided by 5 minus 2.5 J. So again, how do we do this? We have seen how we do this. Find the magnitude, which is 5 squared plus 10 inverse of minus 2.5 over 5. Here where the minus is going to determine or affect my phase. We're going to come to this. Square root of 25 plus 2.5 squared is going to be 5 point, so you have here divided by 5.5 9. The angle. How much is the angle? Tan inverse minus 2.5 divided by 5, which is, you have to be careful here for the angle, right? If you use the calculator, it's going to tell you minus 26.56. Keep in mind that you should know in which quadrant this angle is. Now here, if you go back to the complex plane, I have my x, my real, as 5, and I have my imaginary as minus 2.5. So my angle is expected to be in the fourth quadrant. And yes, it will be minus 26.56 degrees. No, no. It should be minus 26. That's what we're going to use, the angle that is the closest to the x-axis. So in this case, it will be minus 26.56 degrees. And in this case, I would be 10 divided by 5.59, which is 1.79, 1.79, and the angle would be 26.56 degrees. Now, if I go to the time domain, this is the phasor. Remember, the question is asking for IT. Going to the time domain is the opposite of what we have done for the voltage source here. So I have IT
All right.
1.79. Yes.
So when we're trying to find the angle, you just take the numerator minus the denominator to get the angle.
If you make them both from the polar format, then yes. You have to be careful. You have to write to find the correct angle first after you convert them from the rectangular format into the polar format. And then, yes, if you have uh, polar divided by a polar, then you divide the amplitude and you subtract the phase angle. So this one would be now plus 26.56 degrees. See, we got the time domain, we got the time domain signal. So as you can see, the difference here was in the amplitude and in the phase offset. This is the beauty of using the phasor representation and AC steady state. So now if we want to calculate the voltage, V would be this current we found in phasor times the impedance of the capacitor, right? Let's go back to our circuit. This current is going through the capacitor. So in order to find the voltage V, it would be as simple as this impedance of the capacitor times this current. How much was the current? 1.7926. 1.79, 26.56 degrees times how much was the capacitor in polar? Now remember the capacitor in polar would be 2.5 minus 90 degrees right away, right? Because there is no real part. You don't need to, it's a simpler representation of rectangular that has a real part of zero. So right away you can say that this capacitor is also here. If I want to say that this one ZC is also 2.5 minus 90 degrees, right? This minus J is minus 90 degrees. So you can come here and multiply. So this is 2.5 minus 90 degrees. In this case, what do? You multiply the magnitude and you add the phase angle. So in this case, you have 1.79 times 2.5 as 4.47, and the angle would be minus 63.44 degrees volts. Now this is in phasor representation. If I want to go now to the time domain, small letter t equals to 4.47 cosine 4t minus 63.44 degrees. This is volt. Okay. So this is how we do it. Same laws applies. Voltage division, current division, Ohm's law. Same thing. No difference at all. Except now we're dealing with complex numbers. You have to be careful and always remember. Probably I forgot to mention that. But for the capacitor, if you recall, we said that if the here we have the current here as leading the voltage by 90 degrees. So if I if I assume that the voltage as Vm, let me put this one as Vm, uh, phi, then the current would be Vm. This is general, right? This is general plus 90 degrees. So if I am to draw the phasor here of the voltage, let's say this is the voltage, this is phi.
Sir, what do you mean by VM?
That's the magnitude or the amplitude of that signal, which is this is the 4.47 here. Okay, the voltage, the magnitude, voltage magnitude. Then notice the angle for the current. The angle for the current would be phi plus 90 degrees. So this one would be the IM. Sorry, here I put the IM and 90 degrees. So this is the relationship for the voltage across the capacitor and the current into the capacitor. The current is always leading the voltage by 90 degrees. Keep this in mind. Where did I get this one from? From the relationship that I have derived earlier, but here I'm showing it here in general. And instead of taking phi as 0, I just take it a non-zero just to show you. Where did I get this one from? From here. From here. Notice that the phase for the voltage for the capacitor and the phase for the current for the capacitor, there's 90 degrees. The phase of the current for the capacitor is 90 degrees more than the voltage, which means that it is leading the voltage. So the current in capacitors, the current in capacitors leads the voltage by 90 degrees. Remember, I'm talking about the current in the capacitor and the voltage across the capacitor for the same component. Now, if I am to say now this for the inductor, and again, based on what I have derived, I can see that the voltage for the inductor, so if I take this one in general, if I put this one phi, then this one would be phi plus 90 degrees. Now for the inductor, it is the opposite. In inductors, the voltage is leading the current. So if I am to write, this is the current, phi, you will see that the voltage is leading by 90 degrees. The voltage of the inductor across the inductor is has a phase that is 90 degrees more than the current going into the inductor. So current in an inductor is lagging. If you want to use the same statement, then you can say current in inductor lags the voltage by 90 degrees. Or voltage in an inductor leads the current by 90 degrees. Whatever you want to write it should be right. Any questions so far? No questions? Okay.
Sir, there are a few in the chat.
Yeah, you should be able to exactly do what we have done. Basically, in AC steady state, you should be able to do all what you have done in DC steady state. Uh, Find the impedance, the equivalent impedance, use the voltage division, use the current division. So you have to practice solving and dealing with complex numbers. This is extremely important. Yeah. Circuit exactly the same as you've done in DC steady state, you should be able to do it in AC steady state. But now this time it's going to be complex numbers because you have complex components with complex impedances. Okay, so here in this example we need to find the input impedance. He gave you the frequency, the angular frequency omega, because you need this one in finding the exact impedance for the capacitor and the inductor. Remember, we said the capacitors and inductors are frequency dependent components. So in order to do this, the first thing you need to do is to redraw the circuit after you find those impedances. Now you're dealing with impedances. Remember when I said you're dealing with the impedance of the capacitor. You're dealing with the impedance of the inductor. You're not dealing with the capacitance and the inductance. So the first thing you need to do is to redraw the circuit while putting all the impedances on. So the first thing you need to do is to find those impedances. So if I am to call this one C1, just to distinguish between them, and this is C2, then I have ZC1 as minus J over omega. We said omega is 50, omega C1, and C1 here is 2 milli, right? Then ZC1 is minus J. Remember, we said the capacitor will always have negative impedance, right? So what we have here is 10. ZC2 is minus J over 50 times 10 millifarad. ZC2 equals to minus J. Oh, ZL is J omega L J 50 times point 2, right? Which is ZL equals to J 110 ohm, right? So You got the impedances. This one is minus J10. This one is J10. This one is minus J2. All of them are ohms, ohms. Again, be careful. You have to convert them to impedances. If you substitute the inductance or the capacitance into the phasors, that's a major mistake. And now, what do you think the impedance is? Can somebody help here in finding the impedance? Let's call this one, let's call this a branch as Z1, and this a branch as Z2. Any, any help? J10 and 8 are in series. This is correct. So here I have Z1, which is 8 plus J10. And then minus 2J and minus 2J and minus 10J are in parallel. That's not correct. Again, Z2, this branch, Z2 is, what's Z2? Let's take it step by step. Don't jump. Z2 is 3 minus J2. That's correct. So, what is Zn? Give me Zn in terms of Z1 and Z2. Give me Zn in terms of Z1 and Z2. Yes, that's correct. So Zn is minus J10 plus those two impedances, Z1 and Z2, they are in parallel. Z1 in parallel with Z2. That's correct. So what you need to do is find Z1 that is in parallel with Z2. Let me call this one Z3. So Z3 as Z1 times Z2 divided by Z1 plus Z2. So let's do this. 8 plus J10 times 3 minus J2 divided. See, the rectangular format here is very useful when you're adding two phasors here or two complex numbers. So you have here 8 plus J10 plus 3 minus J2. So Z3 is, let's, the top ones in the numerator, we will convert them into polar format. And then, so this is 8 plus J10 because it's easier to divided by 8 plus 3 is 11. J10 minus J2 is plus J8. Now, this one is 8 squared plus 10 squared tan inverse 10 over 8, right? Times 3 squared plus 2 squared tan inverse minus 2 over 3 divided by 11 squared plus 8 squared tan inverse 8 over 11. Okay, so time is over. So this is how you do it. After you, once you find the polar format for the numerator, you multiply the amplitude, you add the phases, and then you have a polar format also in the denominator. Then you divide the amplitude by the amplitude, and you subtract the denominator from the numerator. You will get the Z3. After you do this, you need to add it to the minus 10 minus J10 and find the total impedance. So we will stop here, and then we will continue in next lecture. So all what we have done so far is basically redoing all what we have learned in terms of laws, in terms of rules in DC steady states. However, we are applying them on AC steady states. Okay, so that's what we have for today, and I'll see you on next Tuesday. If you have any question, we have an office hour tomorrow at 12. If you require more office hours, I would be happy to provide more office hours to you. I just need to see your interactions and how useful or how frequent you come to those office hours. So please email me, let me know what you think, and all the best. We'll see you on Tuesday. Have a good day.
Sure.
Yes, go ahead.
You go back a few slides. There was something I noticed that confused me.
Okay, which one?
I think it was when we were first talking about the imaginary numbers.
Which slide?
I didn't write the slide number in my notes. I think you wrote it out on paper. It's after this part, I think. You mentioned z equals the square root of x squared plus y squared.
That's the magnitude. You are going from the rectangular format into the polar format. So the first thing you need the magnitude. You find the magnitude, which is square root of x squared plus y squared. And then the phase would be, if you look here, if this is x and this is y, then the angle we're talking about is this angle, right?
It sounds to me as j is the square root of -1. So if you square that should lead to a negative.
No, 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 no,
No.
no, no, no. You don't include the j into the. You don't have a negative. You don't have an imaginary magnitude. So j is out of the calculation.
Okay.
So you only take the x and the y's, x and y's, right? Here, you only take the x and the y. You don't include the imaginary in the calculation. Only the coefficient of the imaginary number. So this could be negative. It doesn't matter. It's going to give you, you're going to square it. You're always going to get a positive magnitude. And then this angle, the one that we are after, let's call this one phi, is indeed this one, which is the tan inverse of y over x.
Okay. All
Is
right.
that
Thank
clear
you, sir.
now?
Yes. Thank you.
Okay, you're welcome. Okay, so we'll see you on next Tuesday. Have a good day.